Welcome to Lecture 49, which comprises a very brief introduction to the general theory of relativity, the generalization of Einstein's special theory. Why brief? For two reasons. First of all, a number of the other great courses touch on general relativity in astrophysical and other contexts. Second, because the mathematics of general relativity, unlike special relativity, is really quite complicated. It involves very complicated things called tensor calculus. It's differential geometry. It's very difficult to deal with, unlike special relativity, where we could use basically high school algebra to explore what was going on with special relativity. We'll see just a couple of equations in here. I'm just going to present them to you. We won't derive them or anything. So this will be a very brief and non-quantitative introduction to the big ideas of general relativity. So why do we need a general theory of relativity? What's wrong with Einstein's special relativity? Well, first of all, it's special. Now, that doesn't mean it's great and wonderful. It means it's special in the sense that it's limited. It's limited to the case of observers in uniform motion. It doesn't say the laws of physics are the same for all observers, period, but it could. Why doesn't it? Why not the laws of physics are the same for all, period? That would be a truly general theory. So there's a philosophical motivation for general relativity. We would like to generalize special relativity to remove that limitation to observers in uniform motion. But there are some much more precise motivations for general relativity that drove Einstein. First of all, special relativity talks about uniformly moving or so-called inertial reference frames in which the law of inertia is obeyed, in which if an object is subject to no forces, it stays in uniform motion. But how do you know an object is not subject to forces? Some forces are hidden. There are forces like the electric force of the electric field. You can't see the electric field. You can't see gravity. How do you know those forces are or aren't acting? It becomes difficult to identify uniformly moving frames of reference. And it turns out you can identify non-gravitational forces, but identifying gravitational forces turns out to be very difficult. And so the whole edifice of special relativity, if you will, is built on a foundation that isn't very solid because it's built on the foundation of uniformly moving reference frames, and identifying those is going to prove problematic. Second, and another gravitational issue, is that special relativity isn't compatible with Newtonian gravitation. Newtonian gravitation suggests that the Earth sitting here reaches out and instantaneously exerts an influence on the moon or a satellite or the falling apple or whatever. It's a theory of instantaneous action at a distance. And we know that instantaneous transmission of any kind of influence would violate causality under special relativity because it would require an influence to travel faster than the speed of light. And that can't be. So it's not compatible with Newtonian gravitation, and we're going to have to modify gravitation somehow to make it compatible with relativity. So that's going to be the theme of this lecture largely, is how do we develop a theory of relativity that gets around these limitations and that is compatible with gravitation? Well, to make it compatible with gravitation, we're going to have to modify gravitation. And for that reason, general relativity becomes primarily a theory about gravity. General relativity was developed by Einstein pretty much on his own in the years roughly 1907 until it reached its final form in about 1915. And we're going to see what some of the thought processes were that got Einstein to general relativity. Einstein's so-called happiest thought, this was his terminology, occurred in 1907. And it's the idea of what's called the principle of equivalence. And what it says is this. It says, look, you can't distinguish the effects of gravity and acceleration. You get confused about them. That's why we can't tell for sure whether we're in a uniformly moving frame of reference and there are no forces acting, or whether there are forces acting and we're not in a uniformly moving frame of reference. Can't distinguish those two cases. And for Einstein, that became a very happy thought. And I want to qualify that thought a little bit. This is true at least in small regions of space-time, over vast expanses of space-time, or in regions where gravity is extremely strong. This statement of equivalence turns out not to be true, and that's essentially the global reach of general relativity. But in small enough regions of space-time, limited in space and limited in time, then you can't distinguish the effects of gravity from acceleration. That's why it's hard to identify inertial reference frames. Let's look at some examples of how this works. So here I've got a picture. I like to picture an elevator. And the elevator cable has been cut. You can see the cut cable coming out of the top of the elevator. the elevator, with me in it, and with a ball I've been holding, are all in free fall. We're in free fall in the vicinity of the Earth. So there are, in Newtonian terms, forces acting on us. They're the forces of gravity. And we know that the force of gravity gives everybody the same acceleration. We know that the gravitational force, mg, results by Newton's second law in an acceleration g, which is the same regardless of an object's mass. And for years, decades, centuries before Einstein, that was just an interesting fact and coincidence. Einstein made it basically one of the essences of general relativity because the principle of equivalence is the principle that says that's got to be true. So here's what's happening. This situation, free fall under the influence of gravity, looks exactly the same as what would happen if I were way off in space, intergalactic space, far from any gravitating body, and I was in uniform motion, which could mean I was at rest relative to somebody or other in uniform motion, but there's no gravity, and there's no acceleration going on. And if I sit in that now spaceship shaped like my broken elevator, and I take a ball out of my pocket, it will just sit next to me, and I will float free from the elevator floor or the spaceship floor, just like it would in the case of the free fall in gravity, because we're all falling with the same acceleration. In the case on the left-hand side, we have no acceleration whatsoever on the right-hand side, and there are no forces acting. So doing an experiment of finding myself floating around in a spaceship or elevator and taking a ball out of my pocket and putting it next to me and seeing that it just sits there, I couldn't distinguish those two cases. That's what's meant by saying the gravity and the effective acceleration are indistinguishable. Now, you say acceleration, where's the acceleration? Well, let's look at another case. Here's another case. I'm at rest on Earth in my elevator. Now it's sitting there at rest. I take a ball out of my pocket, and the ball falls to the ground with acceleration g. And you'll notice that I'm now glued to the floor of the elevator by the force of gravity. I take the ball out, and the ball accelerates downward. But I could achieve the same thing if I went into intergalactic space. Again, no gravity around. I strapped a rocket engine on my spacecraft, and I fired the rocket engine so it was exerting a force on the rocket that was accelerating it, and if I chose the right thrust for my rocket engine, it would accelerate with acceleration g, 9.8 meters per second squared. If I take a ball out of my pocket and I drop it, it would fall toward the floor. Well, would it really fall toward the floor, or would the floor come accelerating up toward it? The ball would be in uniform motion. No acceleration, no forces acting on it, but the floor would come accelerating up toward it, and consequently the effect would be the same as if the ball were accelerating downward, and I would also find myself pinned to the floor of this spacecraft by that acceleration. So I can mimic the effect of gravity with that acceleration. That's the second half of the principle of equivalence. Those are two situations that experiments done, at least in reasonably small elevators or spacecraft, could not distinguish. That's the principle of equivalence. That's Einstein's happiest thought. So we now have to ask the question, how are we going to describe gravity in this general theory of relativity in which we have this equivalence principle that says, well, gravity is a little bit funny here because we can't distinguish it from acceleration. In particular, if I jump into that elevator in which the cable is broken and the elevator is accelerating downward with the acceleration of gravity, I take the ball out of my pocket, it just floats there. It's as if there's no gravity. I've transformed gravity away by being in free fall. Unless you think that's an artificial situation, it's the situation astronauts right now are in as they're going around the Earth in the International Space Station. They are in free fall. They're moving under the influence only of gravity. They happen to be in a much better state of free fall that doesn't ever intersect the Earth, unlike the hapless person in the falling elevator. But they're in exactly the same situation. All the objects around them are undergoing the same acceleration. It's not that there's no gravity in space, as we talked about way back in Newtonian mechanics. It's that in an object which is in free fall, all the other things around it are also in free fall. They experience the same acceleration, and so it appears that gravity is not there. It appears that gravity is transformed away by that going into free fall. Now, that says, that's just okay, we can understand that. That's just Newtonian stuff. But here's the big philosophical change. We talked in the last lecture about how the only things that are real are the things that don't depend on your point of view. And that means if there's a frame of reference I can get into, and gravity doesn't seem to be there, then what I thought of as gravity, that big massive force pulling me to Earth, is in some sense not real. Now we've got to make another philosophical leap. We've got to decide that all reference frames are going to be equivalent, not just uniformly moving ones. If we make that leap, then when we're in free fall, we're in a frame of reference where gravity has been transformed away. And so we have to ask the question, well, what then is gravity if it isn't that big remote action at a distance force of the mass of Earth pulling me downward or whatever? Well, we can understand that by looking at a larger region of space-time, or in this case, a larger region of space. So here I am again in my falling elevator with the broken cable, except now it's a much bigger elevator, and I'm much bigger, and below me is the curvature of the Earth. So the Earth is small in this picture compared to what it was in the other picture. I notice its curvature, or equivalently, I'm my normal size, and the elevator's my normal size, and this is a really massive object that's been compressed to a very, very small size. Either way. So I take now 2 balls out of my pockets, and I drop them. And they fall, of course, toward the center of the Earth. And so their acceleration vectors are both pointing downward, but down is no longer quite the same direction. That's what I mean by that principle of equivalence requiring a small region of space-time. If you get in a big region of space-time, you'll notice differences in the direction of gravity. And here the direction of gravity is indeed downward toward the center, but that means something slightly different in those different places. And so as we fall toward the center, the distance between those balls, which was pretty far apart when I took them out of my pockets, as I get farther down, that distance gets smaller compared with what it was, because they're falling on these converging paths that go toward the center of the Earth. By the way, you'll notice something else in this drawing. I've become taller, and my arms have become squished horizontally. Why is that happening? It's happening because gravity is also changing with vertical position. It gets stronger as I get toward the center of the Earth, and so there's a weaker force on my head and a stronger force on my feet, and in my frame of reference, that tends to stretch me in the vertical direction. Those forces are called tidal forces because they're what also cause the tides. The tides are caused not by gravity, but by differences in gravity from place to place. And these tidal forces are something I can't transform away by jumping into another reference frame. So those tidal forces, in Einstein's view, are the essence of gravity because they cannot be transformed away, and it's the things that are independent of reference frame that are objectively real. So gravity is about these tidal forces, what Newton would have called differences in gravity from place to place. And again, this is just one quick lecture on the essence of general relativity, so I'm not going to go into many more details about this. I'm going to cut to the chase and give you the description of gravity in general relativity, but it's based on this idea of tidal forces. And Einstein says, well, what really are these tidal forces? What are they really about? What are they really measuring? They're not measuring force, because there is no gravitational force for them to be the differences between, because that can be transformed away. They must be something more essential. And what Einstein says they are is the geometry of space and time. The geometry of that four-dimensional space-time that we already talked about when we introduced the idea of invariance. Four-dimensional space-time now has geometry, and it can be funny geometry, it can be curved. And objects can move in funny ways in this curved geometry, and that's how Einstein's going to explain gravity. So these tidal forces are kind of a residual Newtonian idea which forms the germ of the description of gravity in general relativity. What is that description? The essence of general relativity is summed up in 2 statements. One about where gravity comes from. It comes, as it did in Newtonian theory, from mass, the presence of matter, and energy because of the E equals mc squared equivalence, and I might add pressure, which is a kind of internal energy. We'll get to that when we talk about dark matter and the accelerated expansion of the universe next in a few lectures. The presence of matter and energy changes the geometry of space-time. In particular, it curves space-time. So that's the origin of gravity. Gravity is not a force, it's the curvature of space-time, it's the geometry of space-time. A fancy word for general relativity is geometrodynamics, the dynamics of objects moving in a funny geometry, a curved geometry whose curvature arises from matter and energy. So the presence of matter and energy curves space-time. This is analogous to Newton's statement that mass gives rise to gravitational fields. And here's the equation, and I'm not going to derive this equation, I'm not going to say a whole lot about this equation, but what the equation does is relate something about the space-time geometry, this big capital G with those subscripts Greek mu and Greek nu, talks about the geometry of space-time, On the right-hand side of the equation are some constants, 8 pi times big G, which is that big Newtonian constant of gravitation, and in the denominator, lo and behold, the speed of light comes in to the 4th power. And then this term T with the subscripts mu and nu, and that is called the mass-energy tensor. That is the presence of mass and energy at a point in the universe. So this says right at a point in the universe where the mass energy is described by this T, then the geometry of space-time is described by this G. And you might say, well, this is not too hard an equation. It's just one simple equation relating two things, just directly proportional. But those mu's and nu's can each take values from 1 to 4. They can take 4 values for the 4 space-time dimensions. And so there are 16 possible combinations, and it turns out that only 10 of those are independent. So this is really 10 equations, sometimes called the Einstein field equations. We're not going to go into details, but what it's telling you is how the geometry of space-time arises from the presence of mass and energy. And then the second part of not the equation, but the second part of the description of gravity is that objects then move in the straightest possible paths in curved space-time. And let me give you a diagram and then a quick demonstration of that. So here's an example. This is called an embedding diagram. Don't take it too literally, but what it shows is a massive object, maybe a star, and it shows what you can think of as kind of a rubber sheet that's been deformed by the presence of that star. That's like 4-dimensional space-time. But this is only a 2-dimensional analogy, so it's not a great analogy. And here you see a particle that's moving pretty fast, coming whizzing in from the left, and moving along a path that gets slightly curved because it dips a little bit near that curved space-time, and its path gets influenced, and that is the straightest possible path in that curved space-time. It's not a straight line, but it's the straightest possible path in that curved space-time. And here you see another particle which is deeper in that, if you will, gravitational well, that distorted part of space-time, and it's actually moving around and around and around in a circular orbit around that star. And that's the general relativistic description of both things. The massive star is warping the space-time in its vicinity. The closer you are to it, the more warped it is. And that warped space-time, that curved space-time, is affecting the trajectories of particles. Let's look at a more commonplace analogy for that. Here's a globe of planet Earth. And if I want to go somewhere on this globe, if I want to fly, say, from Egypt, which I've marked on here, to Texas, which is over here, I'm going to follow the shortest possible path. And the shortest possible path is what looks like a straight line, but it isn't really a straight line because it's curved with the curvature of the Earth. In fact, it's what we call a great circle. It's part of a circumference of the Earth with its center in the center of the Earth, and that's the shortest possible path. And that's how airplanes, of course, fly long international distances. And you'll see, even though Egypt and Texas are not that far north, this path has taken us right off the tip of Greenland. That's the shortest possible path, or straightest possible path in curved space-time. And general relativity, in curved space in this case, the flat, the round surface of the Earth being the curved 2-dimensional space, the analogy in general relativity is moving in the straightest possible paths in a curved space-time. Okay, so there is the description of gravity and general relativity. Let's move on to some quick examples of that, some applications of general relativity. General relativity was really obscure through the first 2/3 of the 20th century. It was thought to be right. There were a few tests that suggested it was right, but it wasn't really widely used by physicists. All that changed in roughly the year 1960 to 1970. And today, general relativity has become really the workhorse of modern high-energy astrophysics and cosmology. Let me give you a few examples. So, some consequences and predictions of GR. And what I'm going to do here is give you a sort of old classic, not classical, but an old example, one of the early ones that helped us confirm general relativity, and then talk about what we do with it today. So, one of the first ones was that crack in classical physics. Here we are fixing a second crack, the precession of Mercury's orbit. When you do the calculations of what one body going in orbit around another should look like in general relativity, it turns out the orbit precesses. And it explains very nicely the anomaly of Mercury's 43 seconds of arc per century. And almost as soon as he published general relativity, Einstein demonstrated that indeed that was the case. And so that crack was gone. Today, we have binary pulsars, which are very collapsed stars consisting basically of huge balls of neutrons a few miles in diameter with a mass as much of that as the sun or more, and they're in very tight orbits around each other, and gravity is very strong. And binary pulsars typically will precess at several degrees per year, and that's very easy for us to measure astrophysically. So orbital precession is one consequence and prediction of general relativity, confirmed by Mercury's anomalous orbit, and today used to explain the orbits of massive objects in very tight objects where the precession is quite common, quite easy to observe, quite large. The bending of light. Light travels in the straightest possible paths, but they too are not straight. Light follows the geometry of space-time, and light is in fact bent as it goes near massive objects. So here's a diagram that shows a star that is some ways away from Earth, and in between the star and the Earth comes the sun, and the light from the star that is actually getting to Earth is light that headed out in a different direction than toward Earth because it was bent going around the sun. And that phenomenon was observed in 1919. It had to be done during an eclipse because if you want to look at stars and you want the sun between you and the stars, that's the definition of daytime. Well, so you got to have an eclipse so you can still see the stars. There was a famous eclipse in 1919, the bending of light, which, by the way, Newton's theory of gravity also predicts, but there's a factor of 2 difference in the amount of bending. The bending of light, according to general relativity, was predicted, and it was that, not the publication of special relativity in 1905, that really threw Einstein into world fame. A headline read, "Lights agog in the heavens." Einstein was proved right, verified by that 1919 eclipse. Today, gravitational lensing, as it's called, the bending of light, has become a tool of astrophysicists for all kinds of processes. The picture you see here shows some distant quasars and distant galaxies that are having their light bent, and in fact bent in such a way that they form multiple images or distort the images of the galaxies into these curved arcs you can see. And that's happening because of a more massive cluster of galaxies between us and them. This gravitational lensing tells us something about the intermediate mass. It tells us something about the distant universe. In fact, these gravitational lenses can act as giant cosmic telescopes to allow us to see objects much fainter and more distant than we would have been able to see without them. Gravitational lensing, so-called microlensing, can be used to detect planets as they pass in front of a star. They can be used to detect all kinds of passages of one massive object in front of another by the bending of light and temporary brightening of the light as the light is literally brought to a focus by this so-called gravitational lens. Gravitational lensing is a real workhorse, again, of modern astrophysics. Another example is the so-called gravitational redshift. As light leaves the surface of a massive object, it's like throwing a ball up in the air. The ball slows down and turns around, but light can't slow down. But it does lose energy, and the way it loses energy is by getting to longer wavelengths. So if you have, say, a blue light source on the surface of a very, very massive object, and you look at it from far away, you will see the light shifted toward the red, or even further, maybe into the infrared, maybe into the radio, depending on how massive an object this thing has to climb away from. And another way of looking at that gravitational redshift is it's actually a kind of time dilation, a gravitational time dilation. Clocks, time itself, run slower when they're deep down in a strong gravitational potential, in a strong gravitational field. That was verified by a 1959 experiment, a very delicate experiment was done at a tower at Harvard University. And today, collapsed stars, black holes, neutron stars, even white dwarf stars, which aren't quite so collapsed, all illustrate very clearly this phenomenon of gravitational redshift. Another much more down-to-earth thing that demonstrates gravitational redshift is the GPS satellite system. The GPS satellite system works by timing the passage of radio signals from 4 or more satellites that are in your field of view to your GPS receiver that's in your smartphone or in your car, wherever it is. And by timing those signals very carefully and triangulating, it knows exactly where you are to within, if we're good, centimeters on the surface of the Earth. But because those satellites are up higher in a different strength of gravitational field, if we didn't take gravitational redshift into account, GPS would be off by miles at the end of each day. So we actually have to use general relativity for GPS. Some other consequences and predictions. General relativity predicts ripples in space and time, which we call gravitational waves. We haven't observed them yet directly, but we're searching for them with giant interferometers that are like massive, lengthy versions of the Michelson-Morley experiment, basically, and here we see one in Louisiana, which has a companion in Washington State, and they're looking for coincidences of gravitational radiation as slight difference in those path lengths occur as these ripples in space-time come through. We have sort of seen these gravitational waves as associated with energy loss in binary pulsar systems where the system is radiating gravitational waves. We haven't detected the waves, but the loss in the energy as the orbits change is consistent with what we think the radiation of gravitational waves should be. Another consequence that everyone's heard of are black holes. Black holes actually arise from a mathematical singularity in the solution to Einstein's equations when you worry about what does the gravitation look like around a spherically symmetric object. And if you try to write out something like that delta S squared, that space-time interval that I talked about in the lecture on invariance, you find that there are a number of terms in it, but one of the terms involves the radial distance, and it's divided by this 1 minus r sub s over r. And that r sub s is a constant associated with the mass of an object. And if that quantity in the denominator, if the radius gets small enough that that quantity becomes zero, there's a singularity. The equation blows up, and we want to understand what that means. But that's where black holes originate, and I'll have a little more to say about that. Today, black holes are everywhere. They're in collapsed stars. They're in galactic centers. We know almost all galaxies have collapsed black holes at their centers, including our own Milky Way. And there may even be micro black holes that were formed at the beginning of the universe. So those are some consequences of general relativity for black holes. We'll say a little bit more about black holes in a bit. The whole universe, the cosmic expansion that was discovered by Edwin Hubble in the 1920s, has now been replaced with the large-scale structure of the universe and our general relativistic studies of it. And here's an example of a paper which is called Confirmation of General Relativity. It's a 2010 paper, and it's done by gravitational lensing. So GR is now what we use, general relativity, to describe the large-scale structure of the universe. We even think we have echoes of gravitational waves in the very early universe, and we see them in something called the cosmic microwave background, which I'll talk about more a little bit later. And finally, there's a possibility that dark energy is, in fact, something that could originate from Einstein's equation with an extra term that you see here on the right-hand side of the equal sign. And that term is a term that Einstein first introduced because he thought the universe should be static. It shouldn't be expanding or contracting. So he stuck in this sort of fudge term to make it not expand or contract. Then when Hubble discovered it was expanding, Einstein said, "That's my greatest blunder," and he took that term out. And now, with the accelerated expansion of the universe that I'll be talking about in subsequent lectures, we think maybe Einstein's term belongs back in there. So those are some consequences and predictions of general relativity. Let me summarize and then leave you with a challenge. Special relativity is incompatible with Newtonian gravity. We need a new theory of gravity. That new theory of gravity can't involve instantaneous action at a distance. It can't involve this confusion of acceleration and gravity, or it has to exploit it in a helpful way. That's what the principle of equivalence does for us. Gravity and acceleration are locally indistinguishable, but they are distinguishable in large regions of space-time. The generalization of special relativity that results becomes a theory about gravity, and the essence of general relativity is this idea that mass-energy curves space-time and matter moves on the straightest possible paths in curved space-time. We've seen a lot of applications: precession, bending of light, gravitational redshift, gravitational waves, black holes, and the structure of the universe. Okay, let's end with a little challenge here. The mass of the observable universe, the part of the universe we can see, is estimated to be about 9 times 10 to the 52 kilograms. Find the corresponding Schwarzschild radius, the radius in that equation where things kind of blew up in that general relativistic description of the space-time interval, and compare it with the actual radius of the observable universe, which is about 14 billion light years. Now, I have to tell you something about this Schwarzschild radius. It's the radius at which the escape speed would become the speed of light. If you go back to lecture 13 and look up the escape speed and then calculate what the radius would have to be if the escape speed is the speed of light, you will find that that radius, the Schwarzschild radius, the radius at which that term blows up in that equation, the radius at which you have what's called the horizon of a black hole out of which nothing can escape because the escape speed has become c, you find that that's 2gm over c squared, g being the gravitational constant. from Newton's time, 6.67 times 10 to the minus 11 in SI units. C, of course, is 3 times 10 to the 8th meters per second. Let's work that out. 2gm over c squared, 1.33 times 10 to the 26 meters. Let's work that out. We're going to figure out what that is in light years. That's 1.33 times 10 to the 26 meters divided by 365 days in a year, 86,400 seconds in a day, and the speed of light c, 3 times 10 to the 8 meters per second. That gives us 14 times 10 to the 9 light years, 14 billion light years, the same as the, in fact, observable radius of the universe. Whoa! What does that mean? Does it mean we're in a black hole? Well, not exactly. But it does mean there's some kind of horizon beyond which we cannot see, because at that point the expanding universe is expanding away from us at faster than the speed of light. Whoa, is that possible? Yes, because we're talking about large regions of space-time and the special relativistic restrictions don't apply. So we're kind of trapped in a horizon, somewhat like a black hole horizon, but not exactly. And that thing has a radius of 14 billion light years, and we aren't able to see beyond that. We aren't able to know what's outside of that.